Oh, I have to talk again. I forgot to uh, turn on my mic. Thank you, Puyi. Okay. So sorry. Oh, so I have to speak again. Okay. What? So for today we will cover the phase diagram. Okay. We divided into two. Okay. Uh, um, First is more on the binary isomorphous alloy. So this is a complete solubility of metals. Okay, 100% based on the Hume rotary rules. Okay, so and then the second part is the binary eclectic. This one is not 100% like a lead and stanums lah. Okay, that one is not 100% lah. So that one we will discuss in Hume rotaries. I think you familiar with the phase diagram with the 100% solid solubility lah. Okay, so I'm not sure in mass and energy balance. I think you see this diagram. Okay, so what we're going to cover for this chapter, okay, um, phase diagram of the pure substance, okay, they have liquid and also solid and liquid solids. Okay, there's we're not considering the gas phase. Okay, mostly we will see the graph composition against the temperature. And then we will see the Gibbs phase rules, the degree of freedoms at the triple point. And then what else? Two phase as well as a single phase. Binary isomorphous alloys. This is a complete solubility in solid state. Okay, we will see. I think one of the example is a copper and nickel. And level rules. So we use these rules to calculate the compositions. Okay, so if we know the temperature and also compositions, so we initial concentrations or composition, so we can predict or we can calculate the compound. Okay, in solid or liquid or liquid and solid phase. Okay. And the next part is maybe we will discuss in the next class tomorrow is a binary eutectic alloy system. Okay, so this is a non-complete solubility in solid state. Not really 100%, maybe 30%, 50%. So, how can we know that not complete solubility is based on Hume rotary rules also. So you can refer in the previous chapter, chapter 4. Okay, complete insolubility in solid state. Okay, partial solubility in solid state and invariant reactions. Okay, so this is we will gonna discuss tomorrow. Okay, and also by using a level rules, okay, we will calculate the mass of each phase, amount of each phase, and also composition for of phases. Okay, for the binary static alloy system. Okay. So I hope that you can interpret lah the binary phase diagram ni. What information we can get from the phase diagram? What the information, right? For example, copper, nickel, platinum, tungsten, and copper, and also mercury. Okay. Carry out phase analysis of binary diagram. So you know how to determine the composition for each phase. Okay. Calculate the amount, mass, or weight fractions. Okay. This is important. And also use a phase diagram to define eutectic reaction, hypoelectric, hypoelectric. And I hope that you know how to sketch or draw the microstructure involvement. Okay, because each phase is going to be different, the microstructure development. Okay, so that's one you have to know lah later. Okay. So phase diagram and the terminology, actually the graphical representation of what phase are present in the metal system at various temperature, pressure, and also composition. So this is a general lah, in general, not really lah. It's just a sketch how the phase diagram actually. Okay, they have a triple point here. Okay, single phase, and also they have what is it? Two phase, right? I think this is more related to the phase eutectic diagram actually, this one. Okay, phase eutectic, because there is alpha and beta solid. Okay, uh, okay, later you will see lah this one for the phase eutectic. Okay, it's more to like this one. Okay, okay. Pure substance plotted as a temperature versus pressure, and mixture we plotted as temperature versus composition. Okay, even later in thermodynamics of chemical engineering, okay, the binary system was you will see this binary system in that course, okay, temperature versus composition, and how to calculate the composition. Okay, I think it's on in year 3, I think, for the thermodynamic SKTK2253. Actually is year 3, year 2. Okay, I think it's next semester. Or this semester. No, next semester. Okay. Okay, so what are the information that you can get from the phase diagram? First, of course, represent phase, okay, in metals, okay, different condition, temperature, pressure, and also compositions. Okay, this is question. Composition is a very important, one of the factors that you required to consider, okay, for the binary system, okay. And the T at which different phase start to melt, okay, melting, or maybe binary sometimes if involving the gas, which is going to be evaporation also, okay. But for solid solubility is, I think, it's mostly only melting liquid, and also it's going to be solidified to the solid, okay. T range under which solidification, okay, this one we will know. So from the phase diagram, okay, so this one, right, okay, maybe it's gonna be solidified. This one is a liquid, okay, this one is solid alpha plus liquid. This is 100%, sorry, should be, okay, so just touch. Okay, this one liquid, this one is solid alpha, okay, so it's going to be solidified from the liquid, and then two phase, and also become solid. This one is solid, solid alpha, okay. So for the binary, maybe this one is A, B lah. Okay. This one is 100% 100% pure lah for A. For B, this one 100% for A pure. Okay. So we can know the solidification from liquid to solid, or solid to liquid is melting lah. Okay. And equilibrium solid solubility of one element in another. Okay. This one we can get the information from the phase diagram. Okay. Okay, so what is phase? Okay, just the definition, what is phase, later what is the definition of component, okay, solubility and solubility limits. So before we proceed with the phase diagram of the pure substance and also binary isomorphous, so we have to know the definitions, okay, because like ice, right? So which one is the liquid, which one is ice, which one is two phase, right? Okay, phase is a region in a metal system that differ in its structure composition from another region. Phase are separated, okay, from each other by the phase boundary. So this is the phase boundary. Okay, so this one is ice and liquid. Okay, so meaning there's this one is, we can consider as mixture lah. Two separate phase, although they both are composed of H2O lah. So there's meaning that is a boundary. To easily understand, it's just a boundary lah, phase. Okay. 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 What is it? Component. Okay. Component is a element or compound of the solution or solution in the system lah. Okay. Or for example, solute in solution. What is the component of the solute? Okay. Or solution. Solution is also component. Okay. Component of syrup, H2O and sugar. This component element lah. This is the element. Component of brass. Component. What is the component? Copper and zinc. Okay. That is component. So for binary, if two component, tertiary alloy is they have a three component, quaternary maybe four, and so on so on. Okay, so they have many components, like a complex components. Okay. The third one is a definition of the solubility and solubility limits. Okay, solubility is the ability of the one element to dissolve another element. Okay, like previous one, if you still remember, like defect lah, imperfection, right? Solute, right? But that one is more to replacing or you try to fill in the vacant of the between the atom, right? But solubility is more to the one element to dissolve another element. And solubility limit is the maximum concentration of which only a single phase solution occur. So solubility limit actually when we increasing the temperature, the solubility limit also increase. Like for example, like you do what is it? You mix the water and sugar, right? Okay. Maybe the solubility limit at room temperature is um, what is it? How many percentage of sugar, right? Maybe is around 50% or 60%. But once you heat it that mixture sugar and also water, okay, maybe to 80 degrees C or 100 degrees C, the solubility of the uh, sugar increase in the water. Okay. So for example, this one they have the unlimited solubility of in water is alcohol. Okay, if you mix, so we cannot see any difference in phase, okay, because it's 100% solubility. Sugar has limited solubility. This one, as I told you, okay, maybe 50% or 40% at room temperature. Okay, if you add more, right? If you add more, it's become concentrate. Okay. Oil also is insoluble. So we can see there is a two phase. This is the phase boundary. This is a liquid, and this is oil. This one is water. Okay. Okay. And then what else? Same concept also we apply to the solid phase. This one is a liquid and solid, liquid, right? This one is different compound of the mixture, oil and water, right? Different density. Same concept also apply for the solid phase. For example, copper and nickel is totally soluble in proportions. Okay, like water and methanol. So this one you have to know Hume rotary rules. Y is 100%. Okay, carbon has limited solubility in ions. Okay, up to only 2.0%. Okay, even if you like compound or chemicals. Okay, when you read the SDS safety data sheet, they have a mention about the solubility in other component like water or any solvents. Okay, they mention in SDS. Okay, so if you look at here that solubility limit in the phase diagram, right? Uh, this one water, sugar in water, right? If you look at here that the concentrations actually is below than 65% sugar in syrup. Okay, it's become syrup, right? Okay, below than 60%. But once you increasing the temperature, okay, so the solubility also increase, right? So it's almost, what is it? When you increase the, for example, right, this one, 80%. Okay, if you add about the 80% of sugar, right? Okay, so it's increase. Okay, so you have to remember that when you increase the temperature, the solubility also increase about 80%. Okay. For different component different lah. Okay. This one is only for water and sugar. Okay. Any questions about the phase diagrams, information what we get, and also the definition of phase component, solubility and solubility limits? Any questions? Okay. So I guess everybody can clearly understand what's the definitions. Okay. So we move to the phase diagram of the pure substance and also binary isomorphic system. Okay. So if you look at here that for the pure substance, okay, example water can exist as solid, liquid, vapor, and depending on the temperature and also pressure. Okay. So if you look at here that this is a liquid, vapor and solid, triple point here, right? This is a evaporation line. Okay, when from the liquid, you heat it, it's going to be vaporized, starting to vaporize and become vapor. Okay, this one is after this is actually a supercritical state. Okay, gas behave like a liquid. Okay, and this one if you vaporize, you condense, so become liquid. This one if you solidify, you become. This one is become. Okay. So this is a freezing line. Okay. This one is if you present in terms of pressure as well as temperature and pressure lah. Okay, so this is only for water, meaning that this is a critical point, I think. Critical point. Okay, pressure 760 torr, and this one is 100 degrees C. Okay, this is a critical point. Okay, okay. So this one is the definition three different phases coexist for the triple point. This one is solid liquid, okay, two phase, and this one also two phase liquid and vapor coexist. Okay, so this one, if we present the temperature and pressure, okay, phase diagram for the pure substance, this is for iron. Okay, it's a little bit different. Just now it's water, right? So if you look at here, they have alpha. If you still remember that polyamorphous structure, right? Okay, the definition of polyamorphous, right, is a change along with the temperature changes. Okay, for example, this one, right, if you heat it, okay, uh, from 500 to 1000 something, right, so it's alpha become the gamma lah. Okay, and gamma become the delta. So you have to know this one. So the unit cells or the structure is become changes from BCC to FCC, and FCC will become BCC. Okay, and this one is already liquid, and this is a vapor. What is the temperature? More than 1000, I think. Is more than 3000, I think. Okay, just remember here they have a 3 point triple point, three triple point, right? Okay, because they have a different type of what is it, phase center cubic unit cell, meaning that a different unit cells is changes along with the times. Okay, if we constant with the pressure. Okay, if we constant here pressure, so we can on. Okay, especially pressure around here. Okay, okay. So this is for the pure iron. Okay, let's see the Gibbs phase rules. I think you remember how to use this Gibbs phase rules. Okay, what is it? P plus F equal to C plus 2. Okay, phase plus with the degree of freedom equal to composition plus 2. Okay, so from here, from the degree of freedom, we can know which variable that we can change to maintain that phase lah. Okay, for example, at the two phase system lah, what variable that you have maintained and what variable you can change. Okay, at triple point, what a variable that you can maintain, what variable you cannot change to maintain at the triple point, right? Okay, so give phase rules an equation that give us a number of phases that can coexist in equilibrium in the system. Okay. Degree of freedom indicates no number of variables that can be changed without changing number of phases. Right, it's variables that we can change either T, P, or C. Okay, okay. Solid liquid system, P is assumed to be constants. Okay. So if you look at here, for pure H2O, right, composition, this is okay, just the definitions, just recall back what you have already learned in the mass balance, right, mass or energy balance. Okay, this is phase, degree of freedoms, components. Generally, we know this one and we want to find this degree of freedoms, right? Okay, this one composition for the liquid for one components. Composition is one because it's only water. Okay, and then one phase region. Okay, meaning that P equal to 1. Okay, this one. P equal to 1 and composition 1. So actually, degree of freedom is two variable that you can change, pressure and temperature here, to maintain in this one. Okay, to maintain in this region lah. Okay, two phase. Okay, and how about two phase region? If you look at here, that this is 2 P, and one component only water, so only variable, and another one you have to keep to maintain this one. Yeah, right. For example, you want to what is it? You want to vaporize, right? Okay, from liquid. See, maintain only the temperature, right? But you decreasing the pressure. Okay, or from there to this side. Okay, okay. And two phase region actually is 0, okay, because phase is a 3. So this is invariant point. We cannot change temperature or pressure, okay, to keep in 3 phase. Okay, you have to remember that. So this is the definition of the Gibbs phase rule. Okay. So from this general binary diagrams, okay, we will see the binary isomorphous system. Mostly we are focusing on the Cooper and nickel system because that one is one of the general example for the complete solid solubility in the solid state lah. Okay. Okay. So let's see the binary isomorphous system. Okay. Sekejap eh. Okay, let's we see uh, this one. For the binary isomorphous alloy. Okay, alloy system. If you look at here, isomorphous binary alloy system. Okay. Two element completely soluble in each other in both liquid and solid state. Okay, you have to remember that one. Okay, 100%. So for example, is copper and nickels. This one. Okay, temperature and composition lah. This one. This is 100% for the component B and also component A lah. So you have to define copper and nickel which one A and B. Okay. So generally this one is going to be copper and the rest is nickel. So this is a liquidus. Okay. This one is going to be solid lah. Okay. Solid. This one is a liquidus line. This one is solidus line. So liquid and solid lah. Alpha is we define as a solid lah. Okay. Okay, so this one is a melting point B and this one is melting point A. Okay, so alloy exit as a liquid. This is only liquid. Okay, so only what is it? Only one phase. Okay, so you have to remember that. And this one is only for solid. Okay, this one is solid. Both copper and nickels. Also both copper and nickels. Okay, so but we cannot tell between A and B here actually. Okay. How can we calculate this composition? That's why we need a level rules. Okay. And then two phase, solid and liquid. Okay. In equilibrium. So composition of liquid and solid phase at any temperature can be determined by drawing tie line. Okay. What is the meaning of the tie line? For example, this one. Okay. You know the temperature, right? And then you know the composition, how to determine the composition, right? Now, for example, like this one. So we can know. This is a tie line. Okay, tie line. Tie line connects phases in equilibrium with each other essentially and isotherm. Maksudnya, for example, this one lah. This one isotherm, right? This one. Okay, this is isotherm. Okay, because along with one temperature. Okay, but we can know the different composition. If we know the initial concentration, so that we can know the composition for different this one composition. Okay, for example, if we know initial concentration at 50, right? This one 50%, right? Initial concentration of maybe copper, right? So at what is it? Maybe this one is 800 degrees C. So what is the composition of what is it? Copper and nickel, right? Okay, or the fraction. So from here we can calculate. Okay, here and here. This one in liquid, this one in solid. Okay, so we can. Okay. Okay, so this is the example, the phase diagram binary isomorphous for copper and nickels. Okay, so copper and nickel have complete liquid solubility and complete solid solubility. So if you look at here, that similar atom ready, FCC structure, similar EN, almost close to zero, same valence state. Okay, based on the hemorrhagic also. So if you look at here, that the initial weight percentage, right, for the nickels is around 40%. Okay, this one is nickels, 100% nickels, and this one is 100% of copper. So how can we know the what is it, liquid and solid, right? So just draw the tie line at 100, 1300 so that we can know. Okay, solid is around 58% and liquid around 45%. This one is the composition of liquid and solid. Okay, so we can but the fraction also we can calculate later. I'll show you. Okay, so this one is the what is it, melting point and melting point lah for A and B, right? So 1084 and 104 15 or 1455. Okay, this is a general diagram for the copper and nickel. Okay, so what we can determine from the binary isomorphous alloy copper nickel system. So of course we know the phase, right? Okay, the phase, amount of weight fraction, okay, and also composition into phase region, okay, because from that phase diagram, we, of course, our goals or our targets, we want to find the composition and the fraction for a fraction of copper and nickels for each phases, okay. So we have to know that one. Okay, so how can we interpret that phase diagram? What is the what step that we have to follow? Okay, first locate a temperature and temperature in the diagrams. Draw the tie lines, okay, from liquidus line to the solidus line, as I already show you. Then drop the vertical line to the composition of axis. So meaning that I sketch again. Okay, so like this liquidus to solidus, right? Okay, liquidus solidus, and then draw a vertical line to axis. Okay, so that we cannot. Composition of liquid and solid are given by the intersection of the vertical line in the composition. Just now I show you this one liquidus, this one solidus. Okay, so you know the composition of liquid as well as solid. Okay, easy, right? Okay, 10:45. Okay, so let's see some example. Okay, if you look at here that phase diagram, number and the phase present. If we know temperature and the initial concentration or composition, then we know the number and the phase present. Okay. If you look at here that the initials is 60%, right? This one, and then at 1100. Okay, this is a liquid, not liquid. This one is a solid FCC solution. Okay, and B, if you look at here, we know 1250 degrees and 35. This is the initial composition. Okay, when you mix, you know, of course, you know how many percentage of how many percent in weight copper and nickels, right? For example, 50% or 30%. Okay, you're gonna measure that one. Okay, of course. Okay, so this one around 35, and then bring it to 1250. So it actually is here on the liquidus. Okay, so we know the what is it? What is it? The phase liquid and solid alpha. Okay, if you extend the temperature, it's going to be liquid. Okay, okay. So how about the compositions? Okay, this one is a phase, right? Say for the compositions, okay. If you look at here that for example 35 weight percent, right? This one, so you draw at what temperature? This one, right? TA. So this is a liquid. So meaning that compositions of the liquid, okay, nickels is equal to initial composition of the nickels around 35%, and the rest 65% is for copper. Okay, this one. Okay, so just minus because 100%, right? 100% minus 35. So you can get composition of the copper about 65%. Right. Okay. So how about at 1190? Okay. So 1190, if you look at here, 1190 here. This one, TD. Right. This one is a 100% solid. Similarly, the compositions C alpha equal to C naught equal to 35% of nickel, because same, right? It's the same. Okay. However, for the there's a two phase, right? Okay. How can we determine that compositions? If you look at here, that this one, right? 1250, right? This one 1250. They have a liquid and alpha. The phase is liquid and solid alpha. Okay. But what is the composition? Okay. So if you look at here, right? So just extend the line. Okay. So since this one is a liquid, right? It's touch the liquid line, liquidus line. Okay, just draw the verticals. This one solidus, right? Draw the line. Okay. So CL equal to was it 32%? So nickel is, if you calculate right from here to here is 32% weight percent of the nickels from left to the right. Okay, and the rest, ialah just 100% minus 32. So you can get 30, 35, 32. Okay, 68% is copper. Similarly also for solid, this one right. So 43% is nickel from left to the right. Okay, 43%. Okay, easy right by using level rules. Okay, okay, okay. For this is in general. Okay, I think it's easy. Let's see how to calculate the fractions. Similarly, the composition right, by using the level rules. Okay. Similarly, also by especially for the this one, two phase. Okay, liquid and alpha lah. Okay. Similarly, also we can calculate the fractions. Fraction is composition is the same by using this level rules. And also we will see the microstructure development. Okay, from the liquid to the solid, solid to the liquid when you do solidification or make it a melts that system. Okay. Okay, this one's interpretation of the phase diagram by using level rules. Okay, first you locate composition and the temperature in the diagrams. Draw the tie line. Okay, fraction of the phase determined by taking the length of the tie line to the other phase. Okay, divide by the total length. Okay, meaning that if you have this one, what's the meaning of the number 3, right? Okay, since you already draw the tie line, actually, you have the phase diagram. Right. Just draw. Right. So you draw the tie line from here and also from here. Okay. So for example, if you want to determine the composition of what is it? Solid, right? The fractions. Okay. And this one also have a tie line. Let's draw the tie line. Okay. So meaning that what the meaning of this one determine by taking the length of the tie line to the for the other faces divided by total length. This is a total length. Okay, this is total length. This one A. This one is B lah. And this one is A plus B lah. Okay. So in order to calculate maybe XS or XS solid or maybe XL, right? Okay. So what you have to do is divide this one lah. A divided by A plus B. Okay. Or B divided by A plus B. This is the meaning of this one. Fraction of each phase. Okay. So for solid and liquid, I will show you in details in the next slide. Okay, this is the meaning of you have to divide by total length. This length, the target length divide by the total length. Okay, for solid and also liquid, and times with 100. Okay. If you look at here that the definition of the level rules is the mechanical analogy to the mass balance calculations, right? See, look at here that we have a this one, right? R and S, right? So R divided by R plus S, or S divided R plus S. Okay. Tie line in the two phase region is analogous to a level balance on the fulcrum. Okay, this is the mass. Okay, mass. Okay, so this is how you calculate. Okay, so if you look at here, the general equation for the level rules give the weight percent of the phase in any two phase regions. Okay, so we calculate in the weight percentage because initial composition in weight, right? Okay, so you have to divide by weight. Okay, so if you look at here for the solid, okay, fraction of the solid, this one the solid here in between this line, right? WO, if you look at here that this is WO, initial weight. Okay, WL, you know this WL, right? And WS. So WO minus WL, this one lah, this one minus with this one. So you can get this one, right? You divide by WS minus WL. So actually you eliminate this one, right? You eliminate this one. So that you can get total. Okay. So this one divide by this one, right? So you can get solid lah. Okay. Similarly also for XL. Okay. For XL, since WS minus with WO lah. Okay. So you can get this one, right? Okay. And WS. Oh, sorry. Just now this one you minus WL, you get this one, right? Okay, sorry. Okay, this one SS. Okay, this one S XL. Okay. Okay. So that is how you calculate the fraction. Okay, let's see the example. A copper nickels alloy contain 47 weight percent copper and 50% nickels. So meaning that this one 100% is nickel. Okay, this one is copper, 53% here. Okay. And it's at 1,300. This one. Okay, what weight percent of this alloy in liquid and what percent in solid? Okay, this one is W naught. This one is W naught. This one is WL. This one WS. Okay. Okay. So if you look at here, that initial is for the XS, right? XL's W naught minus WL's. So minus 53. This one you can get around 43%. Right? Divide by this one, maybe around 58 lah. Minus with WL, right? WL this one. So minus 43 times 100. So you can get the answer. Okay. So you can get around 62%. Gosh. Wait percent, okay? Okay. Just refer back the rules. Okay. How about this one? XS. This one is XS. XL. This one is XS. Okay. WS minus with W not. So meaning that 58 minus 53 lah. Divide 58. Aish. Minus 43 times 100. So you can get how many percent? 58%. Or just 100% minus 62%. Yeah. Okay. So you can get 38%. Same. Yes. So fraction of the liquid is what is it? 3846. This one is 38. 38. This one 38. This one, yeah. Okay, the liquid. This one is 60% for the liquid. For the solid. This one liquid is for 38%. Okay. Faham eh? This is a fraction. Okay. That's how you use the, what is it? So how you use the, what is it? The level rules lah. Okay. So the answer is here. That one. Okay. Last before we stop. Okay, almost. Okay, so binary amorphous alloy. Okay, melting and cooling. Okay, for the tutorial we do tomorrow. Okay, for this one, and then we do our phase detective. A pure component system melting occur at well-defined melting. Okay. So if you look at here that a multi-component alloy system melting occur through a range of temperature between solidus and liquidus line. Solid and liquid phase are in equilibrium in T range. So meaning that if you want to from the liquid to the solid, right? Okay, you can see here 100% of liquid. So if I want you to draw, you have to draw if liquid is like this. And then this one is maybe you can draw like this one. The initials are solid present. Okay, small, right? Little bit small. Okay, and then at two phase, the solidified is grow lah. This one is a growing, right? Because of the nuclei. Nuclei is growing. Okay, liquid solution and crystalline. This one is liquid. This one is the solid. Okay, so you have to differentiate. And then after that, this one is become 100 solid. So meaning that you have to draw like this one. Similarly, also if you want to, this one if you want to solidify, if you want to melt, okay, so you have to from the solid to the liquid. Okay, you have to know how to draw this microstructure. Okay, okay. Maybe at this point, okay, how to draw is this one is maybe the first solid is a pure, right? Like this, right? This one is a 100% solid, but here this line, this is a first liquid appear, meaning that you have to draw a big of solid, right? Big of the solid with a minimum what is it space for the liquid because this one is already almost similar like liquid and solid. Okay, you have to know. Okay, this is a primary, we call it a primary liquid. This one is primary solid to appear. Okay, uh, and if this is a definition, binary isomorphous alloy during slow equilibrium cooling. Okay, solidification in two-phase region. Okay, liquid and solid occur gradually upon cooling from liquidus line. Okay, because we want to solidify. Right? So the compositions change gradually. Okay, you can determine by using a timeline. Once you cooling or solidified or from liquid to the solids, okay, nuclear is a form and is a grow, okay, to consume the liquid of the space of the liquid. Okay, so you have to remember. So you have to know how to draw this evolvement of the microstructure, okay, from the liquid to the solid. Okay. So this is another examples. If you look at here that for the copper and nickel, right? This one is a very small because it's just a primary or initials. Solid is a grow, right? And then it's become grow here and become more. Try to what is it? Fill the liquid space, right? And then it's become 100% solid. Okay. So this is the percentage of liquid and also solid, nickel and also combustion of liquid and also copper. Okay. Okay. Any questions? This one we will do tomorrow. Can you can do first after this lah at home. Okay, you do first this one and then we discuss tomorrow. Maybe you can do this one first. Okay. Any questions about the binary isomorphous, how to use the level rules and also microstructure development? Okay. I hope that you can understand. Is it clear? Okay. So since all of you clear, yeah, just to go all clear. Okay, okay, it's clear. So easy, right? Okay. So I hope that you can do this one. Tomorrow we can discuss. Okay, I want to know the answer. So what the phase you can know like compositions, you can calculate phase. What is the this one? And then you have to sketch the microstructure. Microstructure, this one. You do first. Then tomorrow we present. We present. We discuss. This one is microstructure development. Okay. Since all of you is clear already, so we stop this one. I think today we have no discussion. Tomorrow, just discussion about the tutorials. So thank you very much for those who still not scan the attendance. Please scan the attendance. Okay, thank you very much. See you again. Ada lagi yang tak scan ya?